All right, the next section is algebraic graph theory, next part of linear algebra. Okay, suppose we have a graph. It's shown down here. Let's introduce some nomenclature here for it. If we've got a graph, we've got the different nodes there. We usually call those a vertex, vertices. And then the edges are any line that's connecting two vertices. Sometimes we call edges arcs. And I just want to underscore the fact that real-world data is full of graphs. One thing that's very interesting is that we can take a graph, like this one that we have, and we can represent it in terms of a matrix. That's called an adjacency matrix, is one way to do this. The way about it is to label the rows and columns of the matrix based on the values, based on the vertices, and then populate the entries in the matrix. Basically, each entry gets a 1 if there's an edge connecting the corresponding two vertices, or a 0 otherwise. So down here, if you look at it, I've got U is connected to X, and U is connected to V. And if you look over here in the matrix, U is not connected to itself, so there's a 0. But U is connected to V, so there's a 1. It's not connected to W, so there's a 0. But it is connected to X, so there's a 1. On and on and on. Now, an interesting thing about this adjacency matrix is what's got certain properties. One thing is it's symmetric. That is to say, we can take and flip it on its diagonal and still end up with the same thing. So we can take the transpose of that matrix and get the same matrix back. So A equals A transpose. Another thing is that if you go out and calculate the eigenvalues for an adjacency matrix, they're going to have real values. They're not going to be complex numbers or imaginary numbers or anything like that. They're going to be real values. So in essence, this notion of algebraic graph theory, it bridges from linear algebra to graph theory. And of course, you know what we're going to do next. We're going to find some eigenvalues. All right. I've got some Python, again, based on NumPy. And I've got my adjacency matrix, the one that I'd shown before. Let me cut and paste that over here. So if I print out what A looks like, there's our adjacency matrix. And very simply, I'm going to calculate the eigenvalues and eigenvectors. All right, and the results out of this, you see the eigenvalues 2.6, negative 1.37, negative 0.27, et cetera, et cetera. And then the corresponding eigenvectors, there's another array for each of those. Our lambda in this case, we've got 4 eigenvalues, again, 2.651 and negative 1.377 and negative 0.23 and then 273 and then 0. Now, what's interesting is that we can use the eigenvalues to characterize the graph, the corresponding graph. It may be the case that very different graphs end up having the same eigenvalues. That can definitely happen, but even so, we can use it to analyze. So one thing is there's a metric called graph diameter, and that's defined as the longest, shortest path, basically the max number of vertices that you traverse where you don't actually do any backtracking. So you can find out how big is that graph at its widest point, if you will. That's called graph diameter. One of the things you can say is that the diameter of a graph, represented by d, we can say that a graph of diameter d has d plus 1 distinct eigenvalues. So in this case, we had 4 distinct eigenvalues, so that we can say d plus 1 is 4, therefore the diameter is 3. That's great. So now we can start to measure our graph by doing some fairly simple things with the matrix. Now, in terms of graphs, I want to point out that there are some excellent open source graph query engines. One in particular I'd like to point to is called Titan. And the company that's sponsoring that open source project, it's called Think Aurelius. Mateus Brockler and Marco Rodriguez are authors on that. They've got Titan, which runs on top of Cassandra or Apache HBase, Berkeley DB, etc. Basically, if you have your data in some sort of backing store, some kind of column store, then Titan allows you to do graph queries on top of that data in a very efficient way. You can just stream right through the data, stream right through the graph by leveraging some of the features of the column store. Cassandra and HBase are really great for this. Accumulo, I believe, there's also support for that. So Mateus and Marco both have some excellent things they've written along these lines. I've got some links down here. Marco Rodriguez has an article called On Graph Computing, where he really goes through into a lot of detail. I think it's an excellent introduction. And then Mateus has Getting Started, which is an introduction to Titan. He's got a graph of the gods. He uses all the different Greek gods, puts them together. You know, it's a pretty strange graph when you actually look at it. When you really start to plot out all the relationships between the Greek gods, there are some pretty interesting things there. So anyway, Mateus shows doing some graph queries on Greek mythology. Pretty interesting stuff. Now, again, we're talking about going between graphs and matrices by using algebraic graph theory. There's a kind of matrix factorization. You know, we looked at a matrix factorization called QR before, a way of taking a matrix and cutting it into chunks, if you will, and then being able to process those different chunks to come up with some interesting result on the other side. Another type of matrix factorization that's very popular is called singular value decomposition. Much more complex kind of idea, but some really practical uses for this. For instance, it's used to create recommender systems. But singular value decomposition is based on this form of, say we have matrix M as our input. Then we've got three other matrices. You can say that M equals matrix U times matrix sigma times matrix V, and V is in a special form of a conjugate transpose. Without going into a lot of detail, the idea is that if you have your input data in a very high dimensional space, maybe you've got thousands of data points or hundreds of millions of customers in your log files, you want to take a very high dimensional, highly variable set of data points, and you want to adjust it down to a much lower dimensional space. Hopefully, by doing that, you'll expose some structure. You'll generalize from a lot of detail into what are the real important high-level points. So you're exposing the structure in the original data more clearly. That's what SVD does. I'm not going to go into all the details about how to construct the different components, the U and the sigma and the V. There's some great papers about it. One of them that I like in particular is from Kirk Baker. Definitely recommend this one. It's got a great tutorial about singular value decomposition. It actually goes through a whole lot of things, introduction to linear algebra and vectors, and how we get into eigenvalues and eigenvectors we talked about earlier. The main point, though, is that if you take a look at, let's draw this. Say that we've got our input data M, and then we've got times U times sigma, and we've got V, and we'll call that VH. So we've got three components there, and we're basically going to say that we've got some input here equals some there, and then some V. What's really interesting with the way that singular value decomposition works is that you've got your singular values. These are square roots of eigenvalues for a particular matrix. This sigma, this matrix in the middle of it, has in decreasing order the sigma, the singular values, based on the eigenvalues. It has them in decreasing order on the diagonal. And then it's got zeros elsewhere. And so what this allows you to do is essentially come in and start lopping off the least important parts. So if I want to, I can take and reduce it down, take all this off, basically knocking out the smallest singular value, the lowest eigen value, if you will. And that's going to be describing essentially diminishing returns on describing the variance. So if you take the least interesting one and lop it off, then you're going to end up reducing down this part here. So effectively, I'm not showing this exactly right, but you get the point that as you continue to drop down this sigma, cutting off the smallest singular values, you cut down the dimension of these parts, and correspondingly, you're going to kind of blur the edges here. So it's a way of going from a very high dimensional space down to a much lower dimensional space and showing what kind of structure, what's the real interesting parts of this. Another way to put it, I think I have a huge lemon tree in my backyard. It's a very prolific lemon tree. Somebody did a graft on this thing a long time ago, but I think it's got some Lisbon stock, but then it's got some Meyer lemon grafts on top of it. And the thing just pops out lemons everywhere. But I have to go in and prune it a whole lot. I always get scratched up a lot when I'm doing that. But it reminds me about singular value decomposition, oddly enough. When you think of a tree, I've got my roots down here on the ground. I've got a trunk, and then I branch out. And then from the branches, there's smaller branches coming out and maybe some twigs. And when I'm pruning my lemon tree, I have to go in there and cut out some of the dead wood, and especially any of the verticals on it. I have to prune these all down. What I end up with once I prune things is essentially the main structure. And that's what we're doing with singular value decomposition. You can take a graph that's very much articulated and has a lot of little twigs hanging off of it and just dial it down so that you just show the main structure in it. You can think of this in terms of a recommender system. If you have 100 million customers, you can represent that in terms of your graph, represent it in terms of a matrix then, and apply an SVD, and then dial it down so that instead of looking at 100 million different patterns, maybe you're only concerned about looking at the top 10 patterns. And that is how you build recommendation systems. Basically generalizing, again, which is a real basis for machine learning. So let's take a look at what this would be. Say that the rows and columns of M, my input data, those represent elements in some graph. So say that I'm serving up cocktails out to a number of different locations. I've got the drones flying out there all over the city, dropping off cocktails with little parachutes. But we've recorded where it is that people are locating particular kinds of drinks. So one side of the graph is all about different drinks. Another side of the graph is all about locations. And you basically come up with this bipartite graph, two parts of the graph, of associating drinks versus locations. And I'm sure that over time, if we calculate or if we collect this data, we're going to end up with a fairly complex graph. But what would be interesting would be to say, why don't we adjust that? Why don't we tune it down a little bit and just look at the main places where, let's say vodka martinis get served off to, Santa Barbara, and maybe, cosmopolitans are being sent off to Chicago. Basically tuning down our graph just to show the main structure. And so what we can do then is apply SVD, essentially using eigenvalues, eigenvectors. We can find out where most of the variation is. We did this before with principal components. And then we can approximate the original data in less dimensions. Again, that's very, very important when you're working with a lot of data, when you're working with a very large graph. So in terms of computational thinking, here's a big idea. If we can represent your data as a graph, a lot of real-world data is graphs, and we can go in then and take the graph in some kind of open source graph query engine, say like Titan. We can go in and test out different insights. We can do our data discovery, validating particular insights that we might have by doing graph queries to prove it. Once we've got some insights, once we know what kind of questions to ask about that data, then let's take it to another step. We'll transform the graph into a sparse matrix. Once we've got a sparse matrix, this might be something really big. So to be able to handle that effectively, we can run something like QR factorization out on a Hadoop cluster. And from there, be able to use the QR factorization to build singular value decomposition. It's one of the main uses for QR. And we might run that on a Hadoop cluster or Spark cluster. It doesn't really matter. The idea is we can use some sort of open source and apply parallel processing and knock down a really big graph, end up with an SVD. Once we've got that, then we can take the dials and knobs inside the SVD. We can adjust the singular values on the diagonal to reduce the graph size very dramatically and just end up with what is the main important structure out of our original data. Be able to see it more clearly. So that's the trick that we're trying to do, going from graphs to linear algebra. So in terms of computational thinking, we can step back and say, OK, this is a good point about algorithm design. Think of our process of organizing data. And then think of a way of adjusting the structure that's in that data. Think about executing on this in stages. OK, we're going to start out with real-world data represented as a graph. And we'll do some graph queries to kind of test out, find if we can derive some insights from that, prove our point. And then if it's indicated, we'll move on to the next step and turn the graph into a big sparse matrix and be able to do some parallel processing on that matrix. So we're taking it in stages depending on what's indicated for business use, as opposed to taking the original data and going directly into your matrix representation. So the point there is apply these different transformations to your data at the appropriate stage. Are you needing to validate insights and just do discovery? Or are you needing to go all the way through to operationalizing your code and running it on a cluster at scale? And the caveat there is you really want to go through it in the right steps.